All right, what I got here is a list of results and as well as the axioms for these things called inequalities, or so these less than symbols, as well as this thing called the absolute value. I wanted to do a little bit of review on this because I feel like some of these properties listed here of the absolute value is sort of forgotten when we come into calculus, and they're so vitally important in calculus that I wanted to spend some time on it in today's or this week's bonus video. And also, in order to understand the absolute value, the definition of the absolute value right here is defined using this thing called inequality. So I also wanted to do a little bit of review on how do inequalities work. Right here, you'll see two axioms for inequality, as well as the literal definition for what this symbol does, what this symbol means. We know that I would go over this. By the way, this worksheet and this PDF is on Canvas or it's in one of the, I think I labeled it like important files or something like that. It's next to the diagnostic test as well as next to the results of calculus file. Really, really important that we study these and are aware of these properties. All right. So the two order axioms say that if x is less than y, then x plus z is less than y plus z. You can add something to both sides of an inequality. I typed this up and I'm going to repeat myself here. To put it simply, the first order axiom says that you can add whatever you want to both sides of an inequality and the inequality will be maintained. Notice I didn't switch this. If I add something to both sides of this. The second order axiom says that if you grab a positive number and another positive number and multiply them, that product will be positive. So these are axioms. What an axiom means is we assume this to be true to get the ball rolling. We have this new symbol. Here's the two sort of rules for the symbol. And here are two more rules. This is more like the definition of the symbol. This is like the rules that the symbol must abide by. We assume that this to be true. We assume that this to be true. That this is true. We assume this to be true, and we assume this is true. And using those assumptions, we prove each of these. Now, like I said, my big goal is to keep these videos short, so we are not going to have time in this video to prove all of these. I actually have a big goal at the end of all this to prove this guy, and that is known as the triangle inequality. So, in order to prove this guy, a few of these results do need to be proven, and that's what I'm going to spend today doing. I think I need to prove this guy down here. So this would, by the way, OL stands for order law. Order law 7. I'm going to spend some time proving that guy. I'm going to spend some time proving this guy. I'm going to spend some time proving this guy. Proving this guy. This guy, some of these will be easy. And then last but not least, this guy. Let's see if we can do it in less than half an hour. I'll be impressed. So we need to see a total of 6 proofs. Let's get going. I'm going to have to be able to move this around. So if I were you, go to Canvas, follow along with me with this PDF, print it out if you so need to, and let's prove all of these. So our first goal, let's prove OL7, and I'll write it down as well. OL7. If x is bigger than 0 and y is bigger than 0 and x squared is less than y squared, then we happen to know that x is less than y. All right, let's see a proof. By the way, in order to prove this guy, we do have to assume that everything prior has already been proven and we know all of these to be true. We will have to use some of those. So, as well as the order axioms at the beginning. So we also have axioms available for us, as well as laws available for us. We only need to assume these to prove all of these. Do these proofs for homework. I think that's a good call. All right. And I will reference them. That's why I brought that up. Suppose x is bigger than 0, y is bigger than 0, and that x squared is less than y squared. Well, I think what that implies is that 0 is less than y squared minus x. Minus x squared. What I just did was I added something to both sides. So I can even say I did that, and that is because of my first order axiom. That's OA1, all right? You can add whatever the heck you want to both sides. In particular, what I added to both sides was negative x squared. X squared minus x squared is 0. We know that by our field axioms. And we have that 0 is less than x squared minus y squared minus x squared. Oh, that looks like the difference of squares. All right, now what I'm going to do is multiply both sides of this inequality by a positive number, okay? Now, so here, let me go ahead and write that down. That implies, here's the positive number I'm going to multiply both sides by. Y minus x times x plus y times that positive number. Now, I claimed that it's positive. That actually comes from the fact that this is positive comes from the results that we have. So let's show that if x is positive, we know that x is positive, and that y is positive, then first of all, x plus y is positive. And if x plus y is positive, then the reciprocal must be positive. Let's show that real quick. So this will kind of be like a lemma. Here, I'll pull up this. X is bigger than 0. Y is bigger than 0. We assume this to be true, which means that, well, first of all, I can add whatever the heck I want to both sides of this inequality. So let me just add y. Add y to this side because of order axiom 1. So 0 plus y is less than x plus y. That's because of order axiom 1. Oh, but that tells me that y is less than x plus y. That is, I guess, because of the identity axiom, field axiom. 0 plus anything is equal to that thing. But look at what I have. 0 is less than y, and y is less than x plus y. By transitivity, which is definition of order, we have that x plus y is bigger than 0. So 0 is less than y, and y is less than x plus y. Therefore, 0 must be less than x plus y. All right. And therefore, I think it's the order law, this guy right here. If something is bigger than 0, then the reciprocal is bigger than 0. It's actually like kind of like a part of this. We get this for free. The reciprocal is bigger than 0, and we're good. So let me go back here. So what law was that? That's OL5. So I'll say, therefore, 1 over x plus y is bigger than 0, and that's because of OL5, order law 5. All right, sweet. So I multiply both sides by an inequality, by a positive number. The whole reason I went through that hoopla is so that I can make sure that I'm not switching this direction. I don't know if you remember, but if you multiply both sides of an inequality by a negative number, this has to switch. We now know that that is not negative, so this can remain the same. And by the way, the fact that if you multiply both sides of an inequality by a negative number is in this. I'm proud of this sheet I made. If x is negative and y is less than z, if we multiply both sides of this inequality by x times y must be bigger than x times z. All right, so if we multiplied both sides of this by x, both sides of this by x, and the inequality had to switch. So try proving OL3 on your own. All it takes are these axioms up here to prove it properly. Fun times. This is real math, by the way. This is like what math is the core of math. So why did I say that? Why did I multiply both sides by 1 over x plus y? Well, on this side, we get 0. Any number times 0 is 0, which also should be proven. 0 is less than, oh, look, those guys cancel, since x plus y is not 0. And what we have is y minus x. And add x to both sides, we get that x is less than y. And I believe that's what we wanted to prove. All right, we did it. So let's go back to our sheet. Check. Let's go to the next one. We need to have a definition of the absolute value. Maybe I can prove them down just like on this sheet. That would be cool. The absolute value is bigger than x. That is not too bad. We do need this result over here, though. If x is bigger than 0, then negative x is less than 0. If x is... Oh, I messed this up. If x is... Oh, well, I only have... Oh, and vice versa. Okay, we're okay. And therefore, if x is less than 0, negative x is bigger than 0. I thought I was missing something, but I had it compactly in here and vice versa. All right. We want to show that no matter what, the absolute value is bigger than 0. In our brains, we're like, well, we've known that forever, but have you proven it? So let's see. Let's prove AL1. And that is that the absolute value of x is always bigger than or equal to 0. Inside of my proof, this is where I'm going to say, try getting that sheet in front of you, because I'm going to reference it without having to move this around so many times, a few times. So proof, recall. The absolute value of x is equal to x if x is bigger than or equal to 0, or negative x if negative x is, if x is less than 0. Okay, so we want to prove that in either case, if x is bigger than 0, or if x is less than 0, in either case, the absolute value is going to be positive. That's actually quite easy. This is almost an immediate corollary of, I think it was OL1. Yep, this is straight from OL1. So case 1, suppose x is bigger than or equal to 0. That would imply that the absolute value of x is equal to x by definition. Absolute value of x is equal to x if x is bigger than or equal to 0. Oh, but that is clearly bigger than or equal to 0. And therefore, the absolute value of x in that case is bigger than or equal to 0. And that is by definition of order. That's the transitivity of order. X is bigger than 0. Absolute value of x is equal to x. Oh, it's not even that. I just replaced this x with absolute value of x. Pfft, never mind, it's not even transitivity or anything. Anyways, case 2. Suppose x is less than 0. That implies that the absolute value of x is equal to negative x. But negative x is bigger than 0. This is because of the first order law, OL1. If you look at the first order law, OL1, it says if x is bigger than 0, then negative x is less than 0, and vice versa. In other words, if x is less than 0, then negative x is bigger than 0, and that's what I just used. Negative x is bigger than 0. And therefore, even if x is less than 0, absolute value of x would actually then be bigger than 0, and of course, therefore, the absolute value of x is also bigger than or equal to 0. So in either case, the absolute value of x is bigger than 0. Bigger than or equal to 0. And that's what we wanted to prove. All right. Let's keep going. We need AL2. AL2. And again, please have that sheet in front of you. This sheet. Let's see the proof. Here's what it says. The absolute value of x is equal to the square root of x squared. Okay, that's actually nice. That's kind of like a new definition for the absolute value of x, and we will use this in the proof of the triangle inequality. We'll use all of these. Let's see what the proof looks like. I haven't done this one in a while, so let's see how I do. I might fumble. I don't know. We'll see. Case 1. X is bigger than or equal to 0. And what we want to show is that this object is the same as this object in that case. Then the absolute value of x is by definition equal to x. All right, so that's important. Now, the square root of star gives the positive square root of star. All right? That is by definition. Always, if you see a square root, it's never plus or minus root star. It's just root star. But the square root of x squared, the positive square root of x squared is just x. And therefore, x is positive. Square root of x squared is also equal to x. Oh, look. Square root, absolute value of x is equal to x, but x is equal to the square root of x squared, because that has to hand us back the positive root. And therefore, in that case, the absolute value of x is equal to the square root of x squared. All right, here's case 2. Case 2, x is less than 0. By definition, then the absolute value of x is actually equal to negative x. X is less than 0, x is negative. To force it to be positive, you put a negative out front. That's how the absolute value behaves. Now, this is actually the same thing. The square root of x squared, this x, the negative x, is going to give us back the positive square root of x, but x is not positive, x is negative. So, positive square root of x squared. So this implies that 0 is less than negative x, and that's going to be our positive. If you don't like what I just said, what you could do is say this. This is the same thing as the square root of... Well, no, that's just gonna botch things up. The square root always passes back the positive root, and therefore this is going to also be equal to negative x. Because x is negative, it's not going to pass back x, right? So if x squared, I think I'm just rambling. I want to be as clear as possible. That's why I'm rambling. But in this case as well, we can say that the absolute value of x is equal to the square root of x squared. And that's it. Therefore, in either case, the absolute value of x is equal to the square root of x squared. I'm going to call that good. All right, next up, we're actually going to use AL2 in this next proof for AL3. AL3 says the absolute value of x times y is equal to the absolute value of x times the absolute value of y. Oh, also an immediate corollary. This implies, and this is actually going to be really important in our proof of the triangle inequality as well, the absolute value of x squared is equal to x squared. That's actually crucial, just by squaring both sides of this. That will be used here in a second. All right, let's prove AL3. We are going to use this result. So let's see it. The absolute value of x times y is equal to the square root of x squared. Oh, excuse me, skipped a step. The square root of x times y squared. All right, and that is because of AL2. Oh, but wait. We know how whole number exponents work. They distribute over multiplication. So this is the same thing as the square root of x squared times y squared. All right, so that's just exponent rules. But x squared is positive. That's actually also proven. We know that x squared is positive by OL4. So if x squared is positive, and we also know that y squared is positive by OL4, look at your worksheet, then we can distribute this radical over multiplication. And also, there's a radical rule. Oh, but we did it already, you guys. That is the same thing as the absolute value of x times the absolute value of y. Again, that's by AL2. We just proved that those two things are synonyms. Done. Slick. All right, let's keep going. We got to keep trudging. How many more do we have? One more. This next one I don't think is too bad. It says that x is always less than or equal to the absolute value of x. AL4. I might bite my words here. I don't know. These are sometimes a little bit weirdly difficult. All right, let's see a proof. I don't think this is actually going to be that bad. There's two cases. Case 1, x is bigger than or equal to 0. That implies that the absolute value of x is equal to x, which implies that the absolute value of x, or I'll say this, that implies that x is less than or equal to, well, first of all, we have that they are the same, and therefore x is also definitely less than or equal to x, or absolute value of x. So we know they're equal, and therefore they're also less than or equal. Or equal. All right, easy peasy in that case. Case 2 might be a little bit more of trickiness. If x is less than 0, that implies the absolute value of x is equal to negative x. But also, negative x is bigger than 0, and that is because of our first order law. Look at the worksheet. If x is less than 0, then negative x is bigger than 0. Okay, so look at what we have. We have 0 is, or excuse me, we have x is less than 0. 0 is less than negative x. Okay, but negative x is equal to the absolute value of x. And we did it. What that implies by definition of order, transitivity, x is actually less than, strictly less than absolute value of x, but that of course also implies that x is less than or equal to absolute value of x. Therefore, in either case, x is less than or equal to the absolute value of x. Okay, we come to the big victory, and I'm 24 minutes in. Let's see, 6 minutes to prove the triangle inequality, AL5. This is something we will have to use all the time with our epsilon delta proofs. Really important video here. We want to make sure that this is actually true. And here's how we're going to do it. Well, here's what AL5 says. X, the absolute value of x plus y, is always less than or equal to the absolute value of x plus the absolute value of y. Okay? Really crucial. Let's see a proof. The first few steps are going to seem crazy, but let's check this out. I'm going to start with this. What is the square of the absolute value of x plus y? That is going to be equal to simply x plus y quantity squared, okay? Now, how did I just do that? I got rid of the absolute values on the inside. That's one of those things I mentioned in green up here. This is always true. So that's all I used. I just replaced x with x plus y. This is true for all x values. And again, that was a result from this OL2 right here. Immediate result. So that's all I've done. Oh, but we know how this works. This is the same thing as x squared plus 2xy plus y squared. Okay, that's huge. But here's the thing. Another thing I know is that x times y, so here, I'll do it in my sort of brain here. X times y is less than or equal to xy. Okay? And that is because of what we just proved right here. I'm just replacing x with x times y. So what I can say is that this is less than or equal to x squared plus 2 times the absolute value of xy plus y squared. Oh, wait, but don't I have another name for this thing right here? Yeah, I do. That's OL3, or excuse me, AL3. So here, let me reference, I haven't justified this one. This was because of AL4. This guy is equal to x squared plus 2 times x in absolute values times y in absolute values plus y squared. I've proven that one too. In this video, that would be AL3. All right, this is fun. This next one, x squared, is the same thing as the absolute value of x squared. That is also that same little green bit right here. X squared is the same thing as the absolute value of x squared. Same thing with y. Y squared is the same thing as the absolute value of y squared. Let's use both of those. I guess that's really like a corollary of AL2. All right, absolutely huge. Check this out, guys. This is the same thing as the absolute value of x plus the absolute value of y all squared. So, therefore, let me summarize this inequality we have right here. We started with this, says it equals this, but this is less than this, which is the same thing as this, which is the same thing as this, which is the same thing as this. So, to summarize, we have x plus y in absolute values all squared is less than or equal to, and that less than or equal to comes right here, the absolute value of x plus the absolute value of y quantity squared. Okay, but check this out. But notice, the absolute value of x plus y is bigger than or equal to 0. That is because of AL1. That's why we needed that one. And since x, the absolute value of x, plus the absolute value of y is also bigger than or equal to 0, I did a little proof of that way at the beginning here. Look at that right there. If x is bigger than 0 and y is bigger than 0, it doesn't matter. In this case, we had absolute value of x, or what I want to use, and the absolute value of y. Follow this logic, and you'll get to the exact same result right here, that the absolute value of x plus the absolute value of y is also bigger than 0. So why am I even mentioning this? It's a good question. And therefore, so what I just said was that the thing inside of this square is bigger than 0. And the thing inside of this square is bigger than 0. And we needed that to happen. I'll say this is sort of because of, I don't know, OL1. and other stuff. It's that blue argument I just had. All right, so why am I saying that these things have to be bigger than 0? Because here's what I have. So here's the 3 statements. I have this statement. I have this statement. And I have this statement. And if you look at OL7, I'll write it down because it's so crucial. OL7 says that if x plus y is, or excuse me, that's not what I wanted to say. OL7 says if A, I'll use A's. If A is bigger than 0 and B is bigger than 0 and A squared is less than B squared, then A is less than B, and we proved that at the very beginning. That was the first thing we proved in this video. So what is you should look at this and think about what our A character is. I think this guy is our A character. Oh, look, it's bigger than 0. We showed that it definitely is bigger than 0. Our B character is this guy right here. That's definitely bigger than 0. And we also have that this thing squared right here is less than, we have less than or equal to. We should consider the odd case that one of these are equal to 0 and see how this looks. Sorry, where was I saying? Oh, yeah, our A character here squared is less than our B character squared, which means that we can go from this part of our law to this part with these 3 statements. This statement resembles this statement. This statement resembles this statement. And this statement resembles this statement. And therefore, with those 3, we can go to this statement, but let's just write it in terms of what we have here. And that is going to complete the proof. We can, quote unquote, root both sides, and giving us that x plus y is less than or equal to the absolute value of x plus the absolute value of y. And that completes our proof of the triangle inequality, the goal of this entire video.